check, 1, 2, 3. Check, 1, 2. Second mic, check, 1, 2, 3. Check, 1, 2. Test, 1, 2, 3. Checking, check. Mic number 2, check. Check. Checking, 1, 2. Test.
So today we're going to talk about zero net energy buildings, and we have 3 instructors from the PG&E Pacific Energy Center, which is a resource very close to us here over on Howard Street. And we focus on commercial building energy efficiency. We're publicly funded, so you can come to the Energy Center and learn more about energy efficiency for commercial buildings, which we're going to talk a little bit about today. And I'm Ryan Stroop. I'm in charge of the existing building classes at the Energy Center. And I have 2 of my colleagues here today. We have Bill Burke, who's our architect on staff, and Pete Shoemaker, who's responsible for the renewable energy portion of our curriculum. So the idea today is to establish how to design a zero net energy building. I know that Michael's been talking about this, Tom has been talking to you about this, but I wanted to establish a few principles just to start, and then I'm going to turn the presentation over to Bill. I'm going to also explain now kind of what we have planned for the day. So the first thing we need to understand for a zero net energy building is just how much energy is the building that we're going to design going to use, all right? So we have this term called energy utilization intensity, EUI. You'll hear that a lot today. So if we look at the amount of energy a building would use in a year for just a typical traditional building, that's a starting point for this. And Bill's going to sort of take this information and determine, again, how to approach Z&E. So consider this as annual energy use. So this vertical axis, this is like a bar chart. We're looking at energy. I'm going to ask you some questions here. How would you, and let's say this is just an office building, pretty typical office building like, say, the Salesforce building here in San Francisco, pretty new office building. How would you expect a building of a different type of the same square footage to use energy? Like if we compared, so let's say this is an office building. How would you expect something like a warehouse on a per square foot basis? How would a warehouse use energy compared to an office building? Would it be more energy intensive or less? Less, good, exactly. So a warehouse would be less energy intensive. Now give me an example of a facility type that's more energy intensive than an office building. Commercial facility type. There's lots of them. Yeah, sure. I want to hear from the students. Thanks for participating. Airport's good. How about a data center? You think data centers use more energy than an office building? Sure. How about a grocery store? Why would a grocery store use more energy than an office building? Yeah, it's the refrigeration. Massive in a grocery store. So we're going to start with the energy use of a building. And then what we have to do from a Z&E standpoint is we want to match that. So we're going to, this is going to be usage. All right. So we have a certain amount of usage, energy that we use in a year. And then we have how much the building itself can generate. All right. So in a Z&E building, we want these 2 things to balance. The first approach, though, is to reduce the usage. It wouldn't make sense, for instance, take an inefficient building and power it with expensive renewables. So we want this to go down. So maybe we have a reduced energy use for our building, right? And then we're going to match that with the amount of generation the amount of power the facility can generate in a year. And Bill's going to talk more about this. We want the usage in a year to match the generation in a year, all right? So Bill's going to help us understand in his presentation how to estimate the usage of a building and for different facility types. We're going to go through some examples of that, all right? That's the first part. What Pete's going to do, and Pete again is our renewable energy expert, what Pete's going to calculate is how much power can we generate based on the site and the potential facility square footage. So say you've got a facility out in the Central Valley. It's got a massive site and a lot of land. You can probably generate a lot more power, say, than an urban building, like this is a pretty big site here, but a typical building that doesn't have a lot of roof area, you're not going to be able to generate as much power. So what Pete's going to do is figure out the capacity. How much can we generate? So for instance, if we have a capacity that exceeds the amount of generation we need, then we're in great shape. We don't have to put PV on the entire roof. But what if our capacity is less than what we need to generate, using dashes here to sort of distinguish, this is all power, but what if our capacity is less than what we need to generate? Should we just, not build the building? Oh, good, she laughed, she's listening. Yeah, no is the right answer. So what should we do? We need to make the building, we need to go back to the drawing board here, make our building more efficient and reduce the amount of power that we need. Or you could find other places to put the generation. So that's our agenda for today. We're going to talk about how much energy buildings use, and that's going to lead to an understanding of how much power we need to generate. And then Pete's going to take some information and some software that you're going to connect online. So it actually is helpful if you are connected to the internet, and figure out how much power can we generate with a sort of generic site. And then in the end, we're going to compare the capacity to the amount of power that we need. Does that make sense as an agenda for today? All right. So I think with that, I'm going to turn it over to Bill.
Hi, everybody. My name's, as Ryan said, and as you can see up there, my name is Bill Burke. I'm a licensed architect in the state of California. Can you believe it? And I've been licensed since 1990, worked on a lot of big buildings, worked actually on hospitals, labs, and I've been, for the last 20 years or so, I've been working on educating other architects about how to do more energy efficient buildings. So just want to reiterate or sort of go over some of the things that Ryan said, and also just clarify a couple of points. So as Ryan said, the general definition, certainly the definition that we use primarily as designers, is net zero energy site. So what that means is the building site. We're not talking about the cost of the energy. We're not going to get caught up in where the energy, if it's grid supplied, is coming from. You can get definitions of those. I'll mention a few of them in a moment. But as a designer, you don't really have a lot of control over those other things. So we're really, as Ryan was saying, we're talking about how much energy, what's the demand for energy of this building, and then what can you generate on either the building itself or on the building site. So I also want to clarify that most zero net energy buildings are going to be connected to the electric grid. So it doesn't mean that they are not drawing electricity from the electric grid. If the building does not have batteries, and at this point most buildings do not have batteries, although that's just beginning, we might sort of be on a tipping point there. But if the building does not have batteries, since PV, which is, I actually wondered, we're energy geeks, so we tend to start using terms like PV, and I thought, I wonder if they know what that means. It means photovoltaic. So it's a photovoltaic panel, so a solar panel. So if you hear us unconsciously use the term PV, it means a photovoltaic electric panel, or what you probably think of as a solar panel on a building. So, since solar energy or solar panels produce energy from sunlight and light, what month of the year would you imagine that a given solar panel is going to produce the most energy? Let's say we're in Arizona. So it's not cloudy, it's not foggy like San Francisco. The panel produces, when sunlight strikes it, what month do you think is going to be when that panel will produce the most energy? June or July, yeah. It's going to, basically, if the sun is in the sky for more hours, that panel is going to produce more electricity. So then, conversely, what would be the month when you would get the least output from that solar panel? Okay, yeah, December. So what that tells us is that we're trying to get to zero over the course of a year. So the solar panels are likely they're going to produce more energy in the summer, like May, June, July. So to really get to zero, in most cases, you're looking at producing more energy than the building needs in the summer. And then likely you won't be able to completely produce enough energy in the winter to run the building. But if you look at a year's worth of energy, the surplus that you generate in the summer is going to balance out the shortcoming in the winter. Now, so that's why most zero net energy buildings have not had batteries. So it's, in a way, I say to people, zero net energy is an abstraction. So it's like you're basically saying, I'm going to take this summer surplus and use it to balance this winter shortcoming. But you can't really store that summer energy until the winter, even if you have batteries. So just, I want you to realize that most buildings actually still have a grid connection. And then the other thing is, to get to zero net energy, you really have to, as Ryan said again, focus on efficiency. So there's something called the CBEX survey, which CBEX, and we'll get into this in a little bit. CBEX stands for the Commercial Building Energy Survey. And it surveyed buildings, and it was done by the U.S. Department of Energy. And they looked at a lot of buildings, non-residential buildings, in the early 2000s. And the CBEX database was released in 2003. So they look at all these different buildings, building types. So you can look at CBEX and say, what's the average energy used by an office building, or the average amount of energy in a year used by kindergarten through 12th grade school, or a grocery store, and you'll find that information in that database. So if you assign that value as like being in the 100th percentile, and it's going to vary depending on the building type, you're going to have to get probably 70% below what the average building in 2003 used to have a shot at getting to zero net energy today. So when I say 70% reduction, we're really talking in relation to this CBEX database from early 2003. So I think this kind of just reiterates what I'm saying. And this is assuming you don't have battery storage, so it's really just saying you can, if you produce more energy than you need in the summer, it gets fed into the electric grid and somebody else can use it. And then at night, if the sun isn't out, your solar electric panels are not going to be using any energy, or producing any energy. So without batteries, you're drawing off the electric grid at night and then potentially in the winter. And if you do have, we could have a whole other discussion of this, but if you have natural gas in the building, since most of our buildings now, many of our buildings still use natural gas, you would have to convert it all to, we convert it to KBTU, British thermal units. So how many thousands of British thermal units does your building use per square foot? So it's a metric, and I'll come back to that metric. So I put this slide up here just so you're aware of this if you run into this. As I mentioned, as a designer, you're mostly gonna focus on net zero site, but you may come across these other terms: net zero source, net zero cost, net zero emissions. So net zero source is actually going back to the source of the energy that you're using. So California actually has a relatively clean grid, electric grid. We don't burn coal in California to generate electricity. In some areas of the U.S. And in other areas around the world, they do generate a lot of electricity from coal. So if you go back, so net zero source is basically sort of saying, how much energy is being used at the generating plant, and how much of that is, what's the total efficiency coming to my building? As a designer, you have no control over that. So again, my point is, as a designer, you're aiming for net zero site because that's what you control. As Ryan pointed out, you control how much energy your design is going to require for the building to operate, and then you can control how much renewable energy you can put on the building. You don't control the source of your energy. Similarly, you may run into net zero cost. So, from a building owner's perspective, you're typically not looking to produce more energy. You don't want to give your energy away. So from the building owner's perspective, you may be focused on net zero cost, but again, that's going to depend on things like utility rates and things like that. As a designer, you don't really have much control over that. Now, net zero emissions, meaning greenhouse gas emissions, you can also get into that, but again, that's going to sort of depend on where your electricity is coming from. Was it produced from coal, natural gas, or is it coming from a windmill? And one thing that is beginning to happen at the policy scale is we are sort of beginning to move from net zero really to net zero emissions, because to combat climate change, we want to limit emissions in the end. So, but for now, as a designer, you're focusing on net zero site. So if you do see these other terms, don't get confused. You want to focus on net zero site. Again, so what we're showing here is, I'm just sort of trying to make the point that, as you make the building more efficient, which is the blue line coming down, thank you. You want to make the building efficient, then you have to add enough renewable energy to meet the demand that you still have. So one way to think about this, again, if you're looking at a building site, is you want to make the building efficient. You want to add solar. I mean, in some cases you could do wind, but in most cases we're looking at solar. Add it to the building. Now, in some cases, in an urban setting, that may be all you've got is the building site. But in a suburban or rural setting, you may have a parking lot. So you could, how many of you have seen covered parking with solar panels on them? Anybody seen that? Yeah, okay. So if you're in an area where you have a lot of parking and you either can't get the building to be efficient enough, or here's another thing to think about. I've got a one-story building and I can put solar on the roof. Well, what if I have a four-story building? Did my roof area necessarily get larger? No. So I have the same amount of roof area if I have a four-story building, but I have 4 times the floor area. So you get into this thing of the taller your building goes, the harder it is to get to zero net energy. So again, I think we've made this point that, you've got these building loads, you've got solar panels, and you also draw from the utility grid. And so we're looking at the metric that gets used really as sort of a measure of the density of your building energy use is the number of BTUs, British thermal units, per year, but then you divide it by square foot, by the floor area, the total square footage of your building. The way to think about this is, it's sort of like miles per gallon or kilometers per liter. It's a measure of, how far do I get to go on a given amount of energy. This will come back to really when we get back to what Pete's talking about is, solar produces in kilowatt hours, and then we've got to convert that back to kBTU just to make this metric work. So 1,000 watt hours if you multiply that by 3.142, you've converted it to the thousands of British thermal units, which is the metric that buildings use. Okay, another thing that's going to affect your ability to get to zero net energy is your climate. So recognize this state. So for code compliance purposes, California has 16 different climate zones, so you can see them here on this map. You can kind of group them, but my point here really, be it California or be it another part of the U.S. or the world, climate is a variation. So, So I'm pointing sort of here to climate zone 7, which is San Diego. Climate zone 16, how many people have been up to Tahoe? Have you been to Tahoe in the winter? Does San Diego get as cold? Document that actually was produced by Arup. Arup is a gigantic engineering firm, international. They've got a San Francisco office. They produced this for the California Utilities and for the California Public Utilities Commission. So this is from 2012. They were looking at 2020. So they were trying to estimate how can these building types get to zero net energy by the year 2020? Are there building types that can? Are there building types that can't? What are some of the factors? So I'm just going to run through a few of these, and if you got questions about them, just speak up, okay? And for those of you online, apparently you can send a question electronically. So, and you can download this from the internet and I can get you the links. But so here we're talking about a medium sized office building. So you can see they're saying it's 3 stories tall, and you can see here it says load. So in other words, that's telling you how much energy is needed by the building based on your design. And then the next line, which says solar, is basically, can we get enough solar on the roof of this building to get the load minus the solar to be 0? So what we're seeing here is these are the climate zones. So we're seeing that regardless of climate zone, a 3-story office building should be able to get to zero net energy. Does that make sense? Okay. So if we made this a 6-story office building, what would happen to the load? So we've got a 3-story office building, and what we're saying here is in climate zone 15, or climate zone 3 is San Francisco. In climate zone 3, we need 17.2 kBTU per year. If we have twice as much floor area, we're going to have twice as many kBTUs being used. So if it were a 6-story office building, you might not be able to make it to 0. So that's the point here. So you can sort of see here, they did this for me. They actually said, well, let's look at a large office building, and it's now got 12 stories. So, So the amount of energy needed per square foot hasn't really changed much. But the amount of solar they can get on the roof of this building, it's about 500,000 square feet, and it's 12 stories tall, is actually less than they can get on this building. If you divide 53 by 3, you're going to get, about 18,000 square foot per floor. So you would know you have a roof of about 18,000 square feet. And if you look at this one and divide it by 12, well, we've got, we're going to have less square footage on the roof. So where this has taken us is this building, just because it's so big, can't get to zero net energy. We'd have to make the building super efficient, and with their estimate was that it would be hard to do. So again, so one thing I want to ask you is, there's not. So what we're seeing here is climate is not as big an impact on this, but just remember that number. It's about 25 kBTU per square foot per year. Here, you know, with a school, we're seeing again, school can get to zero net energy, and you know, it's 2 floors. We have a lot of roof area, and so we can put enough solar on the roof to zero it out. You see a little bit more variation in the impact of climate. You know, we're at 22, and here we're almost up at 30. Now, here we have a large hotel. So again, we're saying it's 6 stories tall, and what we're seeing is that the amount of energy a hotel uses, if you remember when Ryan asked you, are there buildings that use a lot more energy? Well, a hotel is one of them. So with a 6-story hotel using a lot of energy, we can actually get a reasonable amount of solar onto the roof, but the building is tall enough and uses a lot of energy. You know, just think of all the laundry that's being laundered, and the people want to be comfortable in their hotels. So, you know, and there's lighting and there's food service. So it's going to be hard to get a large hotel to zero net energy. And my point is the variation in climate zone is still relatively small, but look at that number for your large hotel in relation to your secondary school. So what this is telling us is that on a square foot basis, a hotel uses about 3 times as much energy as a school. And they tend to be taller. So if you've only got a certain amount of roof area, you know, you can get the school to zero net energy relatively easily, but getting the large hotel is another matter, okay? So let's just look at 1 or 2 more. So Ryan asked, you know, what are some building types that use a lot of energy? Well, look at these numbers. The school was 25. You know, if you go into a restaurant, you know, someone said there's refrigeration. Well, there's refrigeration, there's cooking, there's lighting, you know, there's sort of theatrical lighting, if depending on the place. So getting a sit-down restaurant to zero net energy is probably one of the hardest building types. So, you know, we just kind of want you to understand the differences in these restaurants. And then similar, Ryan called out a warehouse. Well, you know, honestly, most warehouses could be net zero positive. They could be producing, you know, they tend to be maybe 1-story buildings, a lot of roof area, not a whole lot of load in there, you know. So a net zero, this is actually one of the very first building types that was identified as warehouses. Could have been net zero energy 10 years ago, no big deal. Okay, so you got your computers. I would appreciate it if you would go to zerotool.org. How am I doing on time? Okay, all right, I'll try and speed up a little. So in terms of estimating your energy use intensity that you kind of want to target, the Zero Tool, anybody heard of Ed Masria or Architecture 2030? Okay, well, check out Architecture 2030. Just go type in Architecture 2030. It's a good, interesting website. They produced the Zero Tool. So the Zero Tool is essentially your estimator. So go to the Zero Tool. So what I actually would like you to do is go to the zero tool and actually then go to zerotool.org/zerotool. And I'm actually going to go there right now. Oh, thank you. So here we are at the zero tool. So the zero tool, is an interactive tool. You have to actually tell it some information about your building. So I'm going to ask you to sort of fill in some of these things. So let's say we're doing a K through 12, kindergarten through 12 school. So let's just call it school. And then it's set up for the United States or Canada. I think they have versions actually for other countries. So let's say we're in San Francisco. So let's start with San Francisco. So let's say we're San Francisco. And we're going to say we're in California. What's the zip code of this building? Okay, 94107. So, and then if you're designing a building, you want to check new construction. All right, and then it wants to know a little bit about your building. So we're going to say it's commercial. Now you get a drop-down menu. I'm going to go through K through 12 school. Okay. I'm actually going to uncheck facility as cooking and just say I'm going to let it default. So let's just say our building is 20,000 square feet. It could be whatever. I mean, depending on the building that you're working on. And now it's asking me, am I working in square feet or square meters? I sadly was raised on imperial measures, so I'm going to say square feet. So, I pretty much have filled in my my info, and you can see here. So then I get to say, well, how much of a reduction in relation to that CBEX database do I want? Am I going to estimate? So I'm going to say 70%. That's kind of a good place to start if you're targeting zero net energy. And now I click here, calculate baseline and target. And it just did it for me. So what it's doing here is it's telling me that average school in 2003 in the CBEX database had an energy use intensity of 74 kBTU per year. And from a percentile basis, if we say that's the 100th percentile, we're then, to get our 70% reduction, we got to get an EUI of 23. So that's basically, that's your starting point. So you would say, if I'm going to design a building and I'm going to use some basic modeling tool, energy modeling tool, I gotta hit about 23, an energy use intensity of 23 as a starting point. So let's just go back over to the tool and let's put in a zip code. Let's change this to San Diego. And let's put in a zip code of like 92102. Well, we've still got no, so really what I'm saying is let's shift the building from San Francisco to San Diego. So remember some of those things that I showed you. Did we see a big change in, yeah, so let's see how much it changes if we say we're going to take this building and do the same thing, but do it in San Diego. So we'll say calculate it now, and it really has barely changed, So in California, by building type, the EUI for a particular building type, certainly it varies by climate, but not that much. So let's do one other change here. So we said it was a school. So let's go in here and change that. Let's call it a restaurant. Let's just call it a fast food restaurant, and let's say we've got 20,000 square feet.
So what do you think is going to happen to the EUI students if we choose a restaurant?
So someone just said it's going to go through the roof. So let's take a look. And we're still saying we want a 70% reduction. So look at these numbers. The baseline back in 2003 was 527 kBTU, and they're saying to get a 70% reduction from that, you're going to be at 158 EUI. Do you think we're going to get enough solar panels on the roof of our fast food restaurant to offset that? Likely not. So yeah, so really I'm just showing you, some of the output from that tool. And I just want to reiterate, that you do want, the goal is always to reduce load. Load meaning, the amount of energy you need to use to, load is like cooling, heating, cooking, things like that. You're always looking to reduce the need for that. And then, obviously passive, if you can do things. If you could add, in a certain climate zone, you may be able to add some exposed thermal mass to just, cool the building down at night by introducing outside air. But that's some passive things. Then you would want to add active systems and make them as efficient as you can. And then you go to adding renewable energy on top. So I think with that, Pete, I'm sorry, just a couple more things, just to give an example. So these are, I'm going to just look at 3 different buildings. So this is an office building in Silicon Valley, and there are actually some case studies of these, which I'll send you links to. And I'm going to talk a little bit about this building if we have time. But the building, they modeled it to be 21.2 kB2 per square foot per year. They actually then measured the year's worth of data. So the building actually got down to 13.5 kB2 when they actually operated it. Obviously, as students, you're looking at modeled EUI. You're not going to actually build your building. So you're looking at modeled EUI, and then you're looking at on-site renewable energy here. They were able to produce 28 kB2 per square foot per year from the solar system. So is this building, is it net zero or something else? What was that? It's net positive, exactly. So this is actually not just net zero, it's net positive. So Here's another example of a building up near Oroville. I guess it's actually in Chico. So this is a case where it was a community college building that had been there since 2003. It had a relatively high EUI of 44, and so they wanted to get this building to zero net energy. They could not do it by just adding solar to the roof. So what they did here was, but it's in Chico, much less dense than San Francisco. They have a lot of open land on the site. They have on-site parking, and so they actually built covered solar panels to shade the buildings. It gets pretty hot, to shade the cars. It gets pretty hot in Chico. And then they added solar panels in the field next to the building. So they were able to produce a lot of on-site energy, 41, because they basically went on the site but off of the building. So, you know, typically we're looking to do it on the building, but certainly if you have, you know, let's say if you said, well, we want to get this fast food restaurant, for, you know, or a restaurant closer to net zero, you're going to be looking at things off the building. So in this case, they had an existing building, was not, you know, quite as efficient as it would be, or as they could make it now, but they added additional renewable energy on site, but off the building. So that's another, you know, just another way of getting to zero. I think with that, I'm going to stop and turn things over to Pete Shoemaker.
Get my slide deck up here. Okay, thank you. My name is Pete Shoemaker. I'm the solar guy. I've been doing renewables for the past 12 years there and extended grid sort of things. So I want to talk to you about some basics, terms that you probably know somewhat about, but I want to make sure that you know exactly what's going on. And I'll tie all this stuff. It started with some really basics about electricity in the grid and talking about how solars works, and then we'll follow up on exactly what goes on with these buildings. So this is going to be a little bit about on solar basics. I think you've heard a lot about it. It's a lot in the news. But let's start here. So there's different types of solar. When people talk about it, it's a general term. We're going to talk about photovoltaic, which is energy produced directly from sunlight, PV. There's no heat involved in anything here there. There's also what's called concentrated solar power, which is when you take sunlight and you concentrate it in some form so it heats up some kind of a liquid, like a trough here. That will then produce steam, and then will drive a traditional generator. So you come solar to heat to steam. Anybody ever flown into Las Vegas recently, and seen that big power tower? There's a big up there with the mirrors, about 1 million mirrors around it, shining on this big thing, glows in the dark. That's a concentrated solar power. That works in large instances, not in small, and it works in places like the desert where there's not a lot of cloud cover. There's also solar water heating, or solar thermal. Basically, you put pipes out in the sun. Sometimes you'll cover them up with some glass in modules that look like PV, but they're a little bit thicker. That is an industry that's not quite as strong as it used to be. It's being taken over a little bit by solar electric and heat pumps, but there's also solar water heating or solar thermal. All that could be sort of under the solar banner. We're going to talk about PV, okay? So first off, I want to talk about exactly what electricity is. So I'm going to do a little bit of demonstration right here. I'm going to take my clicker. I'm going to walk over here, and I'm going to take this book, and I'm going to use the clicker here, and I'm going to push the book like this. So you tell me, what was the source energy of what moved that book? Was it the clicker? It was me. So I'm the source. What would the clicker be? Well, how would you describe its role in that process? What was it? Tool? Transmitter? Yeah, transmitted energy, basically. When I pushed on one end of the clicker, how fast did the other end move? Instantly, just about. So it's an instantaneous transmitter of energy, which is essentially what electricity is. It is not a source. Very important. You kind of know that, but some people get confused. So like a rod or pushing a box here. So basically what it does, you all probably have seen back in middle school the schematic of an electron with the nucleus and all the electrons out there. In a copper atom, there's an electron out there by itself in that orbit, and it moves around. It's kind of free floating. So what happens is that electron is a force is applied to one electron in a copper wire. That electron vibrates a little bit, and it hits its neighbor, which hits its neighbor, etc. Very quickly, ripples through just like a chain of dominoes. Now, I don't know if you knew played with dominoes. I did when I was a kid, but you get an idea that the dominoes transmit the energy from there to there, but each domino doesn't travel. It just falls over. So the electrons don't move. The actual electron that starts out in the windmill is not the same electron that ends up in the light socket. It's a ripple effect. That's really important when I talk about how the grid works and how the accounting of the grid works. So now we've got this grid. So now we've got a transmitter of energy. We need a superstructure. We need a highway across which this energy can flow. And that is a very, very large infrastructure which needs a very large company to maintain it. In the same manner that the state maintains the roads, because it's a big entity, it can borrow a lot of money, but it charges road tax to travel, gas tax or whatever. The utility maintains the grid. So now you've got this, again, what I showed you, a copper wire, these atoms that are rippling through. It's almost at the speed of light, not quite, but it's pretty fast. So now you've got this superstructure maintained called the grid. And it's a superhighway for all electricity. Now, it's a very, very large infrastructure, needs a very large company, and that is why, with regard to infrastructure and utilities, in an area, the utilities are a monopoly. It works out that way, not because we want it philosophically, but because it's a business model. To be able to borrow enough money to put all this infrastructure, you have to go out to the markets and have a guaranteed business model. So they have a guaranteed rate of return within a certain area on the poles and wires, and then they can borrow the money and run a business model. But what travels across the wires is not owned by the utility, just like the state does not own the cars. So we charge a tax, which is called transmission and distribution, T&D, fee for using our infrastructure. So that's really kind of the basics. Now we've got these utility-owned infrastructure, a monopoly in an area, one company, but there's different generators that send the cars. They send little electrons rippling into here, and somebody pulls something out over here. So it's like filling up a lake. If you put a little water into this lake and you take the same amount of water here, you keep the lake balanced, and you can say that you can actually use the same amount of water. And if you pay this person for the water that you take out of here in the same amount, then you can say, I have used water from this person. Now, if it's electricity, and this is a green windmill, and you have firms that do the accounting, that measure how much energy the windmill put into the grid, and making sure that nobody else double counted it, and you pay enough money and send it over here, then you can say that you have 100% green energy. And that's what happens, again, when a building is not able to reach zero net energy, there are other options that the utilities offer that to say, I still want to go green, how can I do it? Well, you do this by this accounting method. So that's why Whole Foods or somebody else could say they're 100% green when they don't have windmills or solar on their roofs of all their stores. They pay for it. So again, that's an interesting concept, but also there's a whole ecosystem of companies that do the verification, which are potential business models, potential job applications. So just again, knowing the ecosystem, you can see what goes on there. You can see where job opportunities are. So the grid runs on an accounting basis. Now you've got users taking this out. And now you've got this idea that the electricity now in everybody's home in this building comes in through a service panel, which is then it's routed by circuits to different parts of the house. We'll use a home as an example here. There is a line, there's a meter here that measures how much you take from the grid, and there's a line between the two, which is very important. This is between the utility side and the customer side. It's also called generation side and load side, supply side, demand side. But there's a big line there, and it's very important economically and legally about crosses that line. So what I'm coming to now is solar, which is what Bill talked about how this building could feed back into the grid. This is the details of what Bill brought up. So now you have a generator on your side of the meter. We'll talk about it on the home scale, but the commercial scale is very similar. And that generator is yours. You own it, you maintain it. The utility does not own it or doesn't read it. So it's on your side of the meter, and it supplies your energy first. So this is generating electricity as much as it can, as much as the sun goes up. Now electricity doesn't flow until there's a draw. That plug the energy is sort of sitting there waiting in a sense until you have a draw, then it flows. So if you have a draw here, whatever energy this may produce goes right to satisfy your home first. If there is a surplus, it will automatically then flow this way back into the grid because all this is wired together. And as soon as it crosses this line and flows this way, this meter will pick it up and it will credit your account in a certain way. That way it's basically storing, if you have excess energy, you're not literally storing that energy because that energy is, at that moment is going into your neighbor's feeder, distribution area, and being used by your neighbors. But it's being stored virtually through credits. So that's the way you can have summer energy stored up in a way, in money, and then you can use it back in the winter when there's a deficit. So if there's a deficit, it'll fill in. So you've got this really elegant net metering solar thing where this thing does all it can, and the utility fills in seamlessly. It absorbs your excess, and it fills in your shortfall. So that's how it all works in commercial buildings, and that's why you don't need to have batteries on the site to do this accounting on a yearly basis. Now, batteries are big in the news, particularly with the power shutdowns. There's a booming market in trying to help batteries. Batteries can add value and help you back up, but the net metering systems don't need batteries. Yes, ma'am. Batteries is just like you have in your laptop or in this thing. It's just a large electrical storage mechanism, small scale, large scale, whatever. Well, there is stuff in there. There's material, like my electric car or Teslas have batteries. A lot of materials in there, and how they're going to be recycled, where they come from is a big issue. And there's a lot of money being put in battery research now. There's going to be a big breakthroughs in batteries. The prices are coming down. Efficiencies are going up. Environmental impacts are lowering. But that's what's going on now. It's a very, very important factor. So I wanted you to get this structure about the grid. So when you hear about solar and the meter spinning backwards and all that, and what Bill told you about summer excess and winter shortfall, this is what it's all about, okay? And you can also then pay other people for green energy. If you can't cover your building 100%, you can still do the right thing environmentally. Okay, so now a PV system generates electricity like any other generator. The PV system is the same stuff that any other generator does. It's just this voltage is a certain level that matches your house, fits your home voltage, comes into your home, main service panel, etc. And it's on your side. Okay, so that's basics of solar PV right there. Electricity, again, you kind of know this, but you want to make sure, again, a lot of times the exactitude of your information is really important. If you make small mistakes in this stuff, it can just throw you way off. So the details of your units, of your mathematics, is something you need to focus on. And so we'll talk about that. Electricity, water pressure, there's a certain amount of pressure in this water. The width of the pipe will do the flow, and the output is the work done. And that's volts, electrical pressure, amps, the amount of flow, amperage, and watts is the output. So that's very correlated. You've seen these equations. You may not use them all the time, but you need to be conversant in them. You got these representations, and then formulas here. These are standard electrical formulas. You need to know how to manipulate these equations just like basic mathematics, and that's very helpful. And then kilowatts, megawatts, et cetera, et cetera. Okay, so same square footage, the same amount of watts. Think of it as a flat two-dimensional thing here with high voltage and low amperage or lower voltage and higher amperage. It's the same thing. Just like you can shape a water balloon if you had a bit of hole in the wall, if the water balloon was skinny, you could scrunch it down, shove it through, and move it. You can adjust this load to suit your purposes on the grid, but it's the same amount of energy, and it's called power. It's an instantaneous snapshot. Then there's power over time. Time is another component, another unit on there. Kilowatts is power. Kilowatt hours, or watts and watt hours, is energy. So it's power over time. So how long you use the energy, or the power, is what you get billed on in the utility. So kilowatt hours is important. Again, power is instantaneous juice, so to speak. Energy is power over time. Another way to look at it is if you had a kilowatt, which is two-dimensional thing here, you could have a sort of a timeline going back in a third dimension with snapshots here, like that. And if you put them all together instant after instant, it looked like kind of like a gas tank with a third dimension. So think of kilowatt hours like a tank of energy, all right? So now we've got power times time is energy. So now there's different types of power. There's DC and AC. It's all really fundamental stuff. You can easily Google it. I'm just going to give you a little structure to hold that information so you don't get lost with it. So this is volts, 0 volts, positive, negative. Direct current is one way. It goes straight positive voltage all the time. Alternating current is a phenomenon best associated with Nikola Tesla back in the 1880s. Figured out if you could alternate back and forth, there's a force field that's created by this alternating energy that transmits energy. And that goes positive and what we call negative. But that's just a convention, but it goes this way. And that's called AC. Now, batteries PV panel, the main thing here is that PV panels produce DC and batteries store DC, but the grid primarily uses AC. So there's a translation going on here, change from one to the other, that happens, and every time you do that, there's a little bit of loss of power. So that's important when you're designing things to try to think about those, energy transformations and minimize them. So you've got that going on with DC and AC power, all right? So now we're going to come to the PV stuff itself, and then we're going to follow with an exercise where you're going to look at some of these panels and design a system yourself and see how much it generates, briefly. So the technology here is called photovoltaic. It's a really unique phenomenon through which a photon of light strikes an electron, starts that domino chain moving, and creates a current. And since there's not much to go wrong, not much does go wrong, and these things last a very long time. The genesis of the PV was the space program. Back when the Sputnik came up in 1958, they used solar panels to power those space vehicles, which is much more effective than having heavy batteries. And all that money that was poured into making them survive in that very harsh environment has come down to produce very reliable panels here. So now we've got PV systems here. And this is just a brief thing that's not something you need to memorize, but it's just a matter of thinking about how this works. This is a block of refined silicon, which is specially made, so it's almost 100% a certain type of mineral. A little bit of phosphorus here, a little bit of boron here. You end up having a lot of electrons that have an excess here, and they want to go back to where these holes are, so to speak. They want to come home. But you put a barrier here, and they can't jump across here, so they're ready to go. And as soon as a photon of light hits here, they're energized to move this way and go back where they came from. And that photon then produces that current, and if you take that current off, that flowing electricity is what you want. Okay, so now what you do is you take this silicon and they make it in a factory and they slice it up and they make it into cells, they wire it up, and they put these cells on a backing with 72 of them or 96 of them or more, put glass on top of it, metal frame to make it safe and long lasting, and put it on a house cell module array. And you can make more, make less, it's very modular, right? So now there's one big important number that you're going to think about when you talk about PV systems that relates to what we're talking about on ZNE, is that what's the system size? So the system size means that it'll produce a certain amount, and that amount then you can extrapolate. So like an engine is measured in maximum power. A 4 kilowatt PV system, this is very small for home, means that under a certain benchmark of full sunlight, and I'll talk about what that benchmark is in a minute, certain benchmark of that, it will produce 4 kilowatts of energy at that moment. And if that lasts for an hour, then it will produce 4 kilowatt hours of energy. Now, you're going to get these slides, right, Ron? Of PDFs of all these slides. So if you want to take pictures or anything like that, great, but we'll get them to you. So far, so good? I'm moving quickly. This is basics. I think you've heard a lot of this stuff. I teach this quite a bit. A lot of people know this, but if they just know a little bit of wrong energy, it can send you, you can miss the bus, and you can be off on a wrong track and be very confused. And that's what I'm trying to eliminate here. Okay. So now I want to talk to you about one other term that's really important, and it really relates to what Bill said about the larger the building, the harder it is to get PV to cover it. The idea of efficiency versus capacity with solar. When you say efficiency in the normal work world, it sounds like a better term. If one worker is more efficient than the other, then you want to hire that person because they get more work done for the same amount of pay. Efficiency in solar means power per square foot. Capacity means total power. Now, this is an older photograph, but it illustrates the point. There's two systems here. It's hard to see in this situation, but there's a small number of solar panels here, and there's a larger number of what's called thin film here. But you can see that this square footage is much greater than this. Both of these systems have the same capacity, but because this one does it in a smaller square footage, it's deemed more efficient. So efficient means higher power per square foot. Now, efficient solar panels, the more efficient they are, the more they'll cost. And there's not, right now on the market, the efficiencies range from about 16% to about 22%. So it's not an order of magnitude. There's some increase in it. You may pay more for that. But if you have a big warehouse, let's say, like Bill said, and you can easily cover your ZNE load, you can buy lower efficient panels for a better price. They'll have the same capacity and the same warranty, and you'll get a good deal. You can actually lower your price and get a really good deal. If you have a high-density building with a short roof space, you want to pack as much power as you can on that roof, so you want to pay for the higher efficiency panels, and that's how it's going this year. All right, so capacity, total power, efficiency, power per square foot. So now, one other piece, and again, not that you're going to be installing solar on here, but a lot of what I found in learning is that you know what you need to know and you know what you don't need to know. So you'll hear terms and say, should I think about that? And you go, I know enough to know that I don't need to know it. So shutting those doors down and focusing on the relevant information is a gift. Some of this stuff you may not deal with on a day-to-day basis, but you know that you don't need to know it or may need to. The inverter changes the DC to AC. It's an important component. Out on the market now, there's just a couple of kinds, and I'll let you know what they are. So there is what's called a string inverter. There's concepts where you have a whole bunch of these modules wired together, and all of the AC power, the DC power that they produce, is inverted at one time in one box to AC. That's called a string inverter because it handles multiple strings. There's issues here about longevity, which means the basic thing of longevity is heat. If you have a lot of heat and cooling, thermal expansion on an equipment, that's going to shorten its lifespan. So what happens is there's a lot of energy in here. Let's say it's 96% efficient. But even if it's that, it's going to lose 20, 30, 50, 100 watts to heat. And that's a fair amount of heat. So because of that heat all concentrated in one box, another option is what's called a microinverter. They said, okay, there's a lot of heat in one box. Let's spread that heat out and make small inverters on each module, like this. And therefore, the heat dissipation in each one of these is not so great, and they could last longer. So both of those products are viable on the market. Here you have almost all AC power. The DC only goes tiny from here to here, and it's all mostly AC. And they're going to produce more if they're tilted a certain way than not. So real basic solar geometry, this is something you really want to know. Solar geometry is really fun. You probably know a lot of it just by living. But for architects, for PV designers, it's really crucial to get an idea of what all this stuff is about. And it's fun to learn. So we've got classes on it. There's classes online. Basically, all the planets were started by one big gas cloud that sort of orbited almost like on a tabletop. So it turns out that all the planets rotate as if they're on the top of a table. And so that's called the plane of the ecliptic. One of them doesn't go this way and this way. They all go kind of this way. The sun shines its rays everywhere. But when you get out 93 million miles away from where we are, any ray from the sun that's going to hit us is essentially like one big arrow. So all the rays from the sun are like parallel. Even though the sun looks like it's shining all over the place, it's like shooting an arrow and catching an arrow. And so the Earth then is tilted 23.5 degrees. This is the plane of the ecliptic. This is the axis of rotation, right? So this would be 90 degrees. This is tilted 23.5 degrees. Therefore, you can see that in our winter up here, we're sort of leaning away. And you notice that if you hit a target, if you're perpendicular to the target, you're going to get more arrows hitting that target than if you're leaning away. So more arrows of light, so to speak, hit the target when we're in our summer, because we're leaning in, than in our winter. So that tilt, since the Earth maintains that tilt throughout the entire orbit, it's like tilted over here on summer, and it stays that way. So we're leaning away in winter and leaning in summer, and that spread of 23.5 times 2, 57 degrees, is why the sun appears to move, right? So where I'm going here is, how do you place and tilt your solar panels to guarantee the maximum amount of energy? And this is all about that. So here you go. That's why we have seasons, is because of the tilt. The sun is actually closer, the Earth is closer to the sun during our winter, but because of the tilt, that's why the variation in climate. And the further north you go, of course, the more tilt is and the more the extreme between summer and winter. All right, so now the point here is you've got a sun that moves in a 57-degree window in the sky, so to speak. And that window of, this is like, imagine that this is from here to here is, here is 180 degrees. This is 57. That window will be about right here in our location from 78 to about 23, whereas in Ecuador, it's going to be from 0 to 23, directly overhead, and in Alaska, it's going to be down there. So you can see that. So now, how do you, if you're going to put your solar panels, what kind of tilt would be the best to guarantee to get the most energy? What do you think about that? If you had a solar module here on the ground, where we go, how would you tilt this thing at what angle to make it produce the most energy? What were you thinking? Come again? 90 to what? This line, or this line? This is the sun is moving. So you want to see this is the solstice. This is the equinox. These are the extremes. This is the midpoint. Would you want to put it 90 degrees to the extremes or 90 degrees to the midpoint? Midpoint, yeah. So anyway, if you tilt, and that is latitude, basically. So what they say is your latitude, if you tilt your panels to your latitude, you're going to get the most average sunlight exposure throughout the year. If you were to tilt them back and catch more of the summer sun, that might be a strategy to maximize your sun in the summer when your utility rates might be more. There's strategies there, but just the physics of what I'm talking about. So that's how, so people then, how you tilt the modules is going to determine how much they produce. So we're going to use all these inputs when you do your project in a few minutes. So this is why I'm telling you about this. Okay, that's so real basic solar geometry. Okay, so that's called azimuth. Azimuth is, okay, so that's called, there's a couple of things here also. When you have the solar modules, let's see if I got a piece of paper here. Cell phone, there we go, use the cell phone. Say this is a solar module, and I'm tilting this on a roof. If I put it up this way and I draw a line right down here, that line will point in a certain direction, and that's be the azimuth. And I want to make that azimuth here to the south because we're in the northern hemisphere and the sun is mostly in the southern part of the sky. So the azimuth is the direction that it's pointing when you draw that line right down the middle. So now the azimuth here with north is 0 and south is 180, that's what we're talking about here. So if north is 0, east is 90, south is 180, and west is 270. If you are facing your modules at 225 degrees, what cardinal direction is that? Northeast, south, north 0, east 90, south 180, west 270. What's 225? Northeast? Southwest, right? Last concept, and then we're going to take a little, I'm going to pass out some stuff, and we'll do a little group project here to try to use all this stuff here. There is a certain amount of the goal here is to try to predict what your solar system is going to produce. That's what we're doing. We're modeling. We're modeling what the energy usage is, and we're modeling what it's going to produce. So how do you do that if you have a system in Alaska, system in Ecuador? Depends on where you are on the planet, a certain amount of sun energy is going to fall on you, right? So the goal here is to try to sum up that sun energy in a constant that you can use to plug in at different parts of the globe. So now imagine that the sun were digital, right? The world was digital. If, you know, Bill Gates ran the world or whatever. The sun was 0, and the sun went then boom. It rose and went right to noon. And it shined noon for X amount of hours, and it went off. It would be easy to calculate. You just take the maximum sun at noon, multiply it by the times of hours, and you could do a real easy calculation for sun energy during a day. But it doesn't do that, of course. So you take a calculus function here, it's kind of cute, and you take this area and you make it a rectangle that's equivalent to this area, and you set this as a constant. So the only variable is this. So this constant is a universal constant called 1,000 watts per square meter, or 1 kilowatt of energy per square meter. So sunlight per area. And that's called peak sun hours, a peak sun hour. So how many peak sun hours do you get during a day? It's like how many gallons of gasoline do you get to run your car? There's going to be more in Ecuador than Alaska. So this number here is around 5 or 6. So that then leads to this, which is a map that measures that for lots of areas of the globe, from satellite measurements, averaged over years, plus ground measurements. So you can see that the colors aren't exactly true here, but this is green right here. This is bright yellow, yellow. You can see that even though Louisiana is further south than Arizona, because of the cloud cover of the delta, it's going to get less sun than these cloudless areas of the desert. So it's a combination of direct sun and also ground measurements. So this has been a great boon for PV, for solar, because it gives you a really good way to predict what your system is going to do, and it makes the cost accounting more reliable. You can sort of see what your return on investment is going to be because you know what's going to produce. With windmills, it's not the case. Wind is very difficult to predict, and it's almost like you have to put a meter on the wind site for 6 months to figure out what it's going to be. That's getting a little better, but it's easier to do solar. So all that's going to factor into how much is your system going to produce? Okay, so let me just reiterate here quickly what we just talked about. Take a little breath. Any questions? And we're going to pass out some papers, and you're going to work together in groups rather than just hearing us talk all the time. Okay. First off, electricity was a transmitter of energy, which then, like dominoes, the actual electrons don't move, but the power is transmitted in waves. The grid is the infrastructure that holds it all together, and it's run on an accounting system. Solar is a generator on your side of the meter that produces the same stuff as this does, but you own it, and then you have this net metering, which uses the grid as basically sort of a virtual storage, like a big battery. Volts and amps equals watts. This is power, which is two-dimensional, and this is then energy, which adds another dimension of time, kilowatt hours, like a big tank of energy. And then we have cell module array, solar, and the idea that you tilt towards the midpoint of your wobble, perpendicularity, or that the tilt does affect how much you're going to produce. And then you got these peak sun hours, which is like a unit of gallon of gas, so to speak, that drives the engine of the solar, and you're going to get more in sunnier areas, and you measure that to help you determine the production. Okay, so let's pass out I'd like you to group up in at least 2 pairs. I think we got about 5 groups here, just next to you. You're going to use your laptop. It needs to be connected to the internet, and we're going to do a little project. You need some paper to write on, some calculations and things. A little math. I'm going to let you sort of work this out on your own a little bit. To stumble around and figure it out. You can do it, certainly. Just to get you thinking a little bit. Okay, so here's our project. We're going to tie in exactly what we talked about here earlier. First off, you're going to divide into teams, pair up. Then we're going to assign building locations, each one, pick one. We're going to determine the available roof size. We're going to use the module spec sheet to see how many modules we can fit on the roof. And then we're going to use a program online that sees how many kilowatt hours per year that they're going to produce, okay? So let's do this right now. And then Ryan and Bill are going to tie this back into energy use intensity and do those calculations from kilowatt hours to kBTUs per square foot. All right, so I'd like you to do, right here, Brooklyn t-shirt, excuse me. Yeah. San Francisco, Redding, Tahoe City, groups. Which one? Is there 2 per group? 3 group. So it's San Francisco. You do 2. You do Redding. You do Tahoe City, and we'll skip Fresno. You do Los Angeles. Okay. All right. So look them up, and now find a zip code and a climate zone number for each. Just a zip code in the general area and what climate zone they're in. Write those down. I mean, again, this is like Google is your friend, right? You guys know how to work the web better than we do. So figure out how you correlate those 2. As long as you're within the general city limits with a zip code, it's fine. There'll be multiple zip codes per city. Oh, yeah. People online, you want to do Fresno? I forgot you were there. Type in a question. I'll be happy to answer it if I can. Everybody okay with the? Yeah. Yeah. There's other ways you can do maybe zip code, climate zone lookup. I mean, you can be creative. You can given enough time, you can certainly do it. I'll keep it moving, but it's just a matter of there's a lot of information that you can put it together and make it easier for you. So you got a zip code? Everybody got a climate zone? Okay, what you got there for LA? What's a typical zip code? Oh, we better give them microphones, right? Yeah, that'd be great. Pass those around. Maybe keep one at the front table.
So for LA, we have 90002 with climate zone 8.
Climate zone 8, okay. There you go. This is what I've got. I think the climate zone, Los Angeles is big enough that it can have a couple of climate zones if you go. So that's interesting. Yeah, everybody got something close to that? Yeah, again, this is just, it's not going to vary too much within a city. Okay, so now you've got that now. Find a zip code climate zone number. People online here. Next, determine the available roof size. We're going to give you a standard roof size right now just because it's easier that way. So there it is. So give me the square footage that's usable here. Simple math, just run the numbers. I'll give people a little time. Again, simple math. A lot of employers I've heard, the application of simple mathematics is where it trips up a lot of people. You know this stuff, but you just kind of make a mistake. It's like calculating the check, 20% on a check, you know. It's, you just don't do it often enough. Your phone does it for you, so you need to be able to do it yourself.
We have 16,000 square feet.
How much?
16,000.
There you go. Yeah, roof size is 20,000 times 0.8 times 16,000. Why do you think I'm using 80% on the roof?
Changeable variables? Like?
No, I mean, you have 100% of the roof. We're literally measuring from edge to edge. But is all of that usable for solar?
No, some of it is utility.
Yeah, and what do you think would be lost? Why would not all of it be used for solar? What would cut into that?
You need to access the roof.
There's access lanes, fire setbacks, parapet wall, shading. Shading is the enemy of solar. Again, this is on average. You can't use every square footage. So that's why I'm making a rounding estimate for 80%. And just back up one thing here, just one more. Of all these cities, which one do you think would have the highest EUI per building and which one the lowest? And what's your thinking behind that? What determines that? What's this stand for? The climate, obviously, right? The more variable the climate, the more extreme the climate, the higher EUI, right? So which would have the highest, do you think? Probably Tahoe City, right? You think? And the most mild would be San Francisco, even LA, maybe. San Francisco probably, because LA would have air conditioning load, right? What do you think, Bill? Makes sense? Yeah, Redding, of course, would have a lot of AC load up there. It's in the hot Central Valley. So again, streams of climate are going to be the determinator, in San Francisco has a very mild climate. Okay, so we got the roof size, all right? 16,000 square feet available. So how much PV can we get out of that? So now we're going to go here. You've got a module spec sheet. I'm just going to give it to you. And it's what modules are. What happens to modules, again, they make modules in the factory the exact same way. But because the modules have some organic components in it, they don't come out exactly the same. They may come out a little bit different. So there's two modules that you have that represents the 327 and the 320. You can see that little spec they have there? On the back, they're exactly the same size. We're going to use the 320s. And then that means that it produces 320 watts. So now, how big are they? And how many can you get on the roof? a little math involved here. So take your time. Again, knowing what the equation is as important as getting the right answer. So how would you go about that? Okay, that's what you're looking for, right? That's the key. Can anybody tell me how many square inches there are in a square foot? Kind of an important number. Or you can do it all in square feet. This involves, of course, converting from square feet to square inches or whatever it is, meters to inches. Very important skills to have. Or know how to use the tools to do it. So the goal is to come out of them with a maximum number for a system size in kilowatts. You're not being tested on this. If you don't know and you have questions, that's exactly what we want. Just figure out what you don't know and you'll be better off afterwards.
You're asking them to get the total number of panels first.
What's that? Yeah.
Panels
Yes, to panels first. The end goal is the total system size, but to get there, you have to have the number of modules or panels that will fit on the roof.
I think they got the number.
Okay. So all right, we'll take it step by step here with the math. Okay, so the first thing is to do what? First step is determine. Then each module produces how many watts? And then, so the total system size would be? You have the number? One module is 320 watts. 914 times 320 is about 292 kilowatts, right? That close? Did I do the math wrong? I could have. No? Yeah, well, sometimes you may have rounded off a little bit. But you see the steps, right? Simple. You know, that's, if you got the equation, the calculators will take care of the math for you. Okay, very good on that? Right. This is what PV designers do. This is what their software will do it very quickly, of course. But you need to know the back end of the software. So now we've got a potential of 292 kilowatts of system size. Remember I told you that's the system size. And then now you have to plug in how much, that's the engine size. And how big is the gas tank? It'll show you how far you can drive with that engine, so to speak. So now that's going to vary depending on your different locations. So now I want you to go into that URL right here and get this program up, okay? I'll do it over here on my system live. Remember that map I showed you with all those those dots with the PV production? This is exactly the program where all that comes from, and what they use for. NREL, yes, National Renewable Energy Laboratory. It's a big government-funded in where's Colorado, right? Yeah, Colorado. Yeah, government does good stuff. Really does. There's a lot of people in government that do great stuff, no matter what anybody says, and this is one of them. All this, they standardize these things. They amass the database with all the whole PV industry uses. Really makes a big difference. So now, you guys know how to do software, so I don't have to tell you how to do this. Go, find your number. What we're going to do is find the how many kilowatt hours per year your system will produce in your zip code location. That's why I made you have a zip code, okay? Yeah, you can see where it is. Right here, put your zip in there. And I'll use ours at our energy center here. Yeah. Again, it'll just give you where it should be. This is our location a few blocks away. And so you go to here. There's some defaults in there. Yeah, put in what you can. And the stuff that you don't see, one thing I want to let you know, see, remember I talked about azimuth and tilt here? That azimuth is 180. What does that mean? Where are those modules pointing with a 180 azimuth? Due south, right? So we'll assume that but this is typically on a flat commercial roof. Now what happens is, just an interesting concept here about how they put them in. If you put modules flat on a roof, you can pack them in together like jigsaw puzzle pieces really tightly. But they're flat, so they have no azimuth. It's irrelevant, right? Why do you think you wouldn't want to put them flat? Give her the mic.
Because you're not getting the maximum amount of sun.
You're not getting the maximum tilt. Now, what happens if you were to tilt them 37 degrees on the roof? What else might happen as a corollary to that you don't want? Okay, so if one module is up like this and the sun's shining this way, what happens to the module behind it? It gets shaded. Shading is no good. So they will. The further you tilt them up to get more production, the more they'll shade each other. And if they shade each other, it drops their production. So you have to separate the rows to account from that inner row shading. And then the less modules you can pack in there. So there's a big trade-off here of interesting about how you're going to pack them in and how much they're going to produce. And also, what other environmental factor might be helped if you tilted them a little bit? Think of like a window. What happens to windows in the world? Do they clear all the time? They get dirty, right? And so if solar modules get dirty, they don't produce. It's just like a clean window. The less light that gets through, the less they're going to produce. So if they're flat and it rains, that dirt's going to go, do what? It's going to sit right there. If they're tilted a little bit, it runs off. So the trick is to tilt them a bit to pack as many as you can in there, but don't tilt them too much. So let's say that typically what they do is about 5 degrees. They can tilt them 5 degrees and hardly have any inter-row shading loss, and they can get that runoff. So that's a long explanation to what I want you to put in for this number right here for tilt, put 5 degrees. And leave it at 180. Okay, so then you got your own zip code in there, and I put system size right here. We got that. What was that? What was our size again? 292, something like that? All right. Okay, so take the mic. Yes, everything. Leave everything else in. There's certain defaults in there that they use from averaging, like system losses and things like that. We can let those go. This is the benchmark industry standard program. So the person who has Reading, how many kilowatt hours a year did you get? Somebody have Reading? The first group, wasn't it? Or, yeah.
Where was the Reading group?
Who's got Reading?
Just read off here. That's on.
It's 390,415.
390
Yeah.
kilowatt hours. Okay, so, and this is San Francisco. Who's the people in LA? Who do you have here? What's yours? Read yours off. What city?
The Tahoe City.
Tahoe City, and how many is that?
We got the 452,000.
452. Got more than Reading.
Yes.
Interesting, interesting. Yeah, what that is a you wouldn't think so. And how much LA? What did you get?
We had 446,000.
Yeah, so Tahoe City gets as much as LA. Can you believe that? One other phenomenon that's just a little bit more electricity, voltage varies inversely to temperature. So what happens is if the temperature goes up, the voltage goes down, and actually above a certain degree, like 70 degrees, solar modules actually produce less the hotter they get. It's completely counterintuitive, but it's because of that heat resistance effect with electrical wires. So if you have a really clear sunny day with average low temperatures like Tahoe City, that's a great solar site. That's why San Francisco, with its clear days and moderate temperatures, is also excellent, even better than maybe some places in the desert because of that really high heat. The desert is still a great place, but California is an excellent place for solar in this place here. Even when it's foggy, the sunlight gets through the fog, and the fog cools the modules down and makes the voltage go up. So again, reiterating the fact that this is a wonderful place for solar, and it makes for some surprise conclusions like Tahoe City getting as much as Los Angeles in solar production. Okay, so now you've got, write down the number of kilowatt hours that you have, okay, for each one. So now that, again, now we've got what we can max out on our roof. Now we're going to tie it back. I'm going to give the mic back to Ryan and Bill, and they're going to tie it back into figuring out how we change that metric and get a common unit so we can figure out the energy usage intensity and see what size buildings we're going to have, okay?
All right. So I think it's back to the whiteboard here. Yep. So you all have different numbers. What we're going to do with your numbers, everybody's going to do this, is you're going to convert your generation into a kBTU number. All right? So I'm actually going to sort of redo this. So the math on this, you've got kilowatt hours per year. So I'm going to just use the 415 up here on the whiteboard. So I have 415,714 kilowatt hours per year. All right? Now, there are 3.41 BTUs per watt hour. This was in one of Bill's slides. Okay? So what we're basically going to do is this is going to cancel out. No, it's watt hours. BTUs per watt hour. So this is heat energy over electric energy. So the watt hours will cancel out, and what we'll end up with is kBTUs per year. That was EUI, if you remember what Bill was talking about, right? He was talking about energy intensity in kBTUs per square foot. So we're going to convert the capacity in kilowatt hours into kBTUs because that's how we understood energy intensity for our buildings. It's a simple conversion. So everybody do this with the calculation you got from PV watts. Just multiply by 3.41, okay? And Bill, would you do this for me? So we'll take the 415,714 times 3.41. Actually, you're the San Francisco. You're going to have the same answer for me. 1,417,584. We'll forget the fractional value, okay? And this is in kBTUs per square foot per year. All right? So that's how much we can generate. So we want to set that number aside. Bill also gave us some different energy intensities for different buildings. Do you remember what he said was the approximate energy intensity in kBTUs per square foot for a school? It's around 25. Do you recall that? And he did a restaurant that was around 150. So we're going to calculate how much energy a school with an EUI of 25 and how much energy a restaurant with an EUI of 150, how much energy do those buildings need in a year? Now, how big is we need a number, because we had was energy intensity per square foot. Do we know the size? Pete gave us this. What is the square footage of our building? That was the area for the PV. The area of the building, 20,000 square feet exactly. 20,000 square, so that's the square footage. So we've got this number, the 1 million for San Francisco. You all should have slightly different numbers. The 1,417,000 kBTUs per square foot per year is how much we can generate. Let's see how much we need to generate for our specific facility type. You follow? Everybody understand that distinction? What Pete gave us was the capacity, how much we could create in electrical energy from PV. What we need to understand is how much do we actually need based on the energy intensity of the building, two different building types that Bill provided. That make sense? All right. So this whole thing is the capacity. We're going to do two examples of the load. I used before load, same thing. So we're going to do the load for the K through 12 school. Okay, and remember this was 25 kBTUs. It was actually a great question for your students, Michael, because we talked about this. How did we incorporate energy efficiency into what Bill did earlier in his presentation? He did something to establish a certain energy intensity. Do you remember? Michael's asking the question, have we incorporated energy efficiency? So let me turn that question back to all of you. Did Bill, when he established that 25 kBTUs per square foot, did he establish some target efficiency? He did. He said we're going to take CBEX and we're going to take 70% of it. So we're 70% of a CBEX typical building. That's where the energy efficiency got incorporated. Do you remember that? All right. So we're taking 25 kBTUs per square foot times 20,000 square feet. That will give us kBTUs. Sorry, this is 25. Yeah, actually, this is independent of square feet. Yeah, sorry. So I put square feet in here. That was a mistake, so just scratch that out. So we got kBTUs, and this is actually square foot year. So take 20, so we'll do the school first. 25 times 20,000, 500,000 kBTUs per year. In this case, the square feet cancels out. So, do we have enough capacity if we had a a school with a 20,000 square foot footprint, do we have enough capacity to generate all the power that the building needs? It's a simple yes or no question. Absolutely, right? In fact, we could more than double the capacity with the PV that Pete sized. Everybody follow that? So would you need to cover your entire roof with PV to be ZNE for this school? No. You could put a playground up there or something, right? Right? Maybe not. Let's do now the restaurant. The restaurant, I'm going to simplify things a little bit. So now let's do the load for the restaurant. Which was 150 kBTUs. It was actually 158, but I'm keeping things a little, I'm taking shortcuts. Bill wouldn't approve, but it's okay. Square foot year times the same area, 20,000 square feet. Somebody punch this into a calculator for me. Square feet cancels out again. It's 3 million. So now we need 3 million kBTUs per year. So what are you going to do as designers faced with that ZNE challenge? Your capacity is less than what your building needs. What are you going to do? Is this where you take your laptop and you slam it on the ground and walk out of the studio in a huff? No. You're going to do something. You're designers. So what's the design solution for this problem? Please, grab a mic.
I have a question. Why is the restaurant so difficult to take care of? I forget.
It's just so much more energy intensive.
Okay.
It's just using on a per square foot basis. It's just
okay.
so much more energy intensive. Remember I started this morning and I said office building versus warehouse. Office buildings are more energy intensive, but something like a data center or a grocery store is more energy intensive than an office building. So a
Because
restaurant,
it's size.
by its nature, is more energy intensive per square foot. So let's think about a restaurant for a second. You got dishwashing, you got refrigeration, you got cooking, all of those very intensive, energy intensive processes, right? So if you're trying to now meet all the energy needs of a restaurant, you're going to need more renewable energy per square foot. So now we just took the same scenario as far as size of the building, but with a different type of building, and we now have a larger need. The load is bigger. We can only generate a little less than 1.5 million kBTUs per year. We need to generate 3 million kBTUs per year.
So just triple the roof size.
All right, so the response in the room was we triple the roof size. Well, we could, and I think Pete talked about this, we could put PV on the parking area, the other parts of the site. We can't actually, like, we can't stack roof because it would shade, right? But we could actually put PV on other parts of the site. That's a great answer. We could use the rest of the site. What else could we do?
What about solar panels on the road that are durable, that have a clear glass?
So we could get adjacent sites or purchase renewable energy from other sites, which probably is not something you're going to be able to do with your design competition. That competition is going to ask you to get all your renewable energy from the site itself. I'm looking for Bill for reassurance there. So getting it from some other site is not going to work, but there's something else we can do. Thank you. What you said is perfect. I was waiting for that response. You can make the kitchen and the restaurant even more efficient. That's right. You got to do better. You got to do better. So you do a restaurant that's even better than a 70%. And I'm going to hand this over to Bill. Did you want to comment?
I just wanted to come back to this thing about the school. So, Ryan said 25 kBTU times a footprint of 20,000 square feet, which was what we just said the roof was. Well, would that be correct if it was a 2-story school? If the school were 2 stories tall, we'd be looking at this being 1 million. So if the school, there's some high schools that, and certainly in an urban area, there could be 3 stories. So if we were looking at a 3-story school and we had 80% of the roof in PV, we're pretty much, so what we're learning there is, You know, as the buildings get taller, you got to remember, you know, this footprint goes up, but you only have one roof. So you could do a 3-story school, and as Ryan was saying with the restaurant, if you had a 3-story school, you'd be a little bit short on your generation to get to 0. So what did Ryan just say? Yeah. So your option would be, I got to go back and make my building a little more efficient if I want to zero it out just using the roof. So that's where you'd have to go and say, okay. So, you know, I don't know.
I think Bill's point, sorry.
Yeah.
Is there would be a bit of an iterative approach here, right? You run these numbers, you don't hit your target, then you got to go back and revisit your design, right? So we expect this is going to be part of what you'll go through in your design projects for your ZNE projects. That's I think what Bill's implying.
Yeah. And I you know, I don't want to endorse any particular piece of software, but you know, I'm assuming as students you're using, you know, Autodesk or some of the plugins to Rhino, or you're using Safari. You know, that software should help you, you know, do some of this stuff. I mean, that software might do some of these calculations. But as Ryan said, it's an iterative process. You know, you got to do what Pete, you know, did to say, well, how much can we generate here? And then, you know, if you did have a parking lot and you said, okay, well, we can't do it on the building, you could say, okay, well, how much of the parking lot area do we need to cover to get to 0? Okay?
As a process, did this make sense? We used a couple software tools, right? Bill used a tool to estimate the energy intensity, and then we used another tool to figure out the generating capacity. So those tools would be, I think, resources you'd want to lean on. But you could do, if you were given a location and a facility type, you could do this. So that's our goal, I should say, is we leave today with you feeling confident enough that you could do this on your own if you were given a location and a facility type. Is that, what's your comfort level with that? Feeling good about it?
So, you know, I'm sort of a more technical architect than a lot of people. But one thing I say, I oftentimes have architects come to me and say, well, explain to me how solar panels work. And which Pete just, you know, to sort of give you the background, explain how solar panels work. What I say to architects, and Pete said this, is you don't really need to know how solar panels work. You need to be able to use PV watts to figure out how much you can generate on the roof, and you need to be clear enough, you know, sort of, as Pete said, know what I don't need to know, but you do need to know, oh, well, if I'm going to use this panel, here's how efficient it is. I'm going to be in this zip code, so I know enough to go into PV watts and say, I'm using this panel in this location. My roof area is this much. I know what I can generate on site. And then similarly, you know, actually now is a good time for me just to show a case study or two. Do you have something else? Okay. So, you know, my point is that as an architect, you know, you do have to do this calculation with PV watts, but then it's really sort of like, you know, if you're using early design software, you would describe your building, you know, 3-dimensionally. You do a design, and then you would use that early software to sort of tell me, well, am I hitting that target that I set? You know, and if not, what do I need to adjust? So, you know, getting to net zero does involve these numbers, but, you know, it's not like you don't really have to know that much about how PV works. And really what you need to know is what are some design strategies that are going to get me to a lower energy use intensity. So, you know, this is actually an office building at the National Renewable Energy Lab. When it was built, it must be close to, I don't know, 8 years old now. It was the largest net zero energy building in the world. So, you know, and this is one of these things where we could talk about the aesthetics of this building. I think it's reasonably successful. But you know, another thing, and I'm almost reluctant to say this, but it's true, because energy and net zero is important. But as an architect, you got to get a building that works, and that kind of works aesthetically, works functionally. I don't know if any of you saw it. There's actually an interesting article in the New York Times this morning on the Stephen Hall library, I think in Queens. And, you know, it's gotten a lot of good press. Well, there are areas of the building that have real accessibility problems. So they were just sort of saying that, you know, there are some real functional complaints that people are making. So you got to get the building to work. So my point here is, you know, as Ryan showed, if the building were 2 stories tall, you could get to zero net energy. You know, if this were $1 million, this K through 12 school were $1 million, and you knew that you had 80% of the roof, well, and let's say you said, well, gee, you know, we actually want to add something that has an area of the building where we have more glass. So we're actually going to increase the heat load a little bit. So you could actually make your KB, your energy use intensity a little higher, because you had some other consideration you wanted to address. You know, maybe you have this, I mean, one thing I've heard about this building up here is it's in Golden, Colorado, and it has these incredible, you know, the Rocky Mountains are right there. So they did an excellent job here of working quite hard to shade these windows. So there's a daylight window above and a view window here. And so these shading devices really knock down a lot of the heat gain. Someone that I know I've never been in the building, but someone that I know who has been in the building said he was a little frustrated because he's outside the building and there are the Rocky Mountains. Now, maybe if you see him every day, this is less of an issue, but he said he lives in California and there are the Rocky Mountains. He said when he went inside the building, if you're lined up with a window, you can see the Rocky Mountains. But he said as you look at the windows to your right and to your left, these shading devices, which are doing an excellent job of cutting the load, he said, really cut off your view to the mountains. And so he said he personally got a little frustrated that here I am in Colorado with these mountains, and I'm in this building that has wonderful daylight. The window up above has all these, it actually has a commercial product called light louver in it. So it prevents direct sun coming through, but direct sun, or really any light, but in particular direct sun that strikes it, is redirected and reflected upward. So, so if you think, where is the light in this building? If you look up at your ceiling, the light, the illumination produced by these circular lamps here, where is it going? Some of it in the center is coming down, but isn't a lot of it going up and then being reflected off of your white colored roof? Well, that's what's happening here, is the sunlight comes in and it's bounced up onto a white roof. They don't need electric lights on, at least when the sun's out. So, so my point here is, you know, I'm telling you to make as energy efficient a building as you can. And I think, as we said, it's going to vary some depending on building type. So with a school, you could say, well, I'm willing to add some load, heating or cooling load, to get a view. And part of the reason I'm willing to do that is that it's going to mean I'm going to need to buy more solar electric for the roof. So it's always a trade-off. But my point is, you know, we're telling you to design an efficient building and to put renewable energy on your building, but we're not telling you that it's purely a calculation. That's sort of what, as the architectural design student, that's your job, is to sort of figure that out. So here's this building. Let me just show you a few photographs of another building. So this is, thank you, Pete. I keep forgetting that the mouse is there. Okay, so this is a building in Silicon Valley. It was an existing building, but it was gut rehabbed, meaning, they sort of stripped it down. It was exposed concrete, can absorb heat generated by the users. So let me just run through here's the roof. So you can see, again, why would you only get 80% of the roof area in solar panels? Well, they added skylights because they wanted to get daylight into the building and distribute it broadly across the building. They also, as Pete was talking about tilt angle of your solar panel, they did an analysis of the openings for those skylights, just to sort of understand when are they going to get direct sun and when are they not. Here's the interior of the building. It's got a good skylight. It's got exposed concrete floors. They're renting it out. It's in Silicon Valley. It's being sort of used by a lot of tech companies. Relatively high occupant densities. People generate heat. The concrete, they open the skylights and the windows automatically at night. When the temperatures drop down, the concrete cools down and then absorbs heat to keep people comfortable throughout the rest of the day. Another thing they've added is, a ceiling fan moving very slowly. I got to tell you, Pete and I work in the same office, and we don't have a ceiling fan, but we got an oscillating fan, and a little bit of air movement makes what would otherwise feel too hot a lot more comfortable. So, by just adding some air movement, really what they've done here is this building they have air conditioning. They actually have, they put, do you know what a package unit is? So they put a package unit, basically it's an all-in-one, air conditioning, heating unit on the roof. But the building is really designed to hardly ever use it. Which another thing that they said is they didn't buy efficient package units. They actually bought sort of minimally code compliant package units because it didn't matter, because they run so few hours a year that it was better to basically buy the minimally compliant version and not spend money for a more efficient one. It made more sense to take that money and put it into the ceiling fan, or to put it into the skylights, or to put it into an architectural finish that would just make the interior more enjoyable to people. So, that's kind of, what we want you to understand is that, your job is to sort of make a nice building that, is also energy efficient and adds renewable energy to get to zero. Does that get my point? Okay. Maybe questions?
So one point I want to emphasize is today was just about sizing and understanding the relationship between load, how much the building uses, and how much you need to generate. I'll be back without Pete and Bill in tow in a couple weeks just to talk about design strategies. We're going to have a whole session on different ways to make an energy efficient zero net energy building. But we're not going to talk about this balance of generation and load. That's really a topic dedicated for today. So I wanted to open it up in our last few minutes here and give you an opportunity to ask any questions of me or Bill or Pete on what we covered today. Understanding that we're going to spend more time together in a couple weeks. A couple weeks, right, Michael? Yep. Any questions about anything from today? Do you guys have some ideas about how to approach this?
I have a question about the windows with the shading on the top and the side. How much does that really save having it on the side? I mean, is it worth it to get rid of the view? Because most of the light would come in from the top, right?
Yeah, so one thing I would say is, as I said, this building is about 8 years old. Not that, the other thing I would say is, it depends on the client. So this was the National Renewable Energy Lab, and one of the things they were trying to prove, if you figure the building opened 8 years ago, its planning probably started 12, 13, 14 years ago. They're really, they wanted a pleasant workspace. They wanted daylighted interiors, they wanted an open plan, and they got a lot of that. They also wanted to prove that you could make a building this big and get it to zero net energy. So, so I think, it is a little bit, it depends on what are your owners or your clients' requirements or goals. So for this particular client, the National Renewable Energy Lab, trying to prove you could make a 250,000 square foot office building that was net zero, which at the time was like, no, you can't really do that. And they were like, we're going to so they were willing to compromise the view to just reduce some of that heating, so. Yeah, I don't know. Yeah. So Pete's question was, is there like a calculation or a number? Honestly, that's the sort of thing where design software should be able to tell you. If you were using something and you said, well, let's shade the windows and see what the EUI is, and then let's take the thing off and see what the EUI is. I don't think it's a super huge amount, but I think given that they wanted to get to zero net energy 10, 12, years ago, they did it because it shaved it, and they were looking for all these ways to shave the demand for energy in that building down. And so, I think for some other client, it may be, I want the view, or pull them back a little more. But for this particular client at that point in time,
So there's a direct relationship between that view and how many PV panels you're putting on the roof, right? If you think about it, it's like one is pretty expensive. The PV is pretty pricey. So if you're doing some architectural decisions that reduce your load, and in many ways that's more cost effective than like stacking more panels on your roof. That's when we talked about this iterative approach, that's what we're really talking about. Your design and what you ultimately do to reduce the load is going to impact how many panels you need. So I think Bill's point's a good one, but it doesn't come for free. Like the view has an energy cost that you have to make up with more panels. Other questions? Thanks. I appreciate the question.
Where do you find the CBEX EUI numbers? Is that for type of buildings? Where is that listed?
Well, you can actually go to the Zero tool will relate back to it. So I think that's the simplest thing is if you go to the Zero tool, it's going to tell you for this building type, here the 100th percentile that you see in that little diagram that it generated is what it draws from CBEX. Honestly, if you just typed in CBEX Department of Energy, it'll probably come up.
Is that still 2003 data you were saying, or they,
Well,
they keep
So
updating that?
here's the thing: is that there are a couple of things here. So for a long time, the Department of Energy EPA Target Finder referenced CBEX 2003. Architecture 2030 issued what's called the 2030 Challenge, which called for reductions, the goal being that by 2030, architects are designing buildings that through efficiency and added on-site renewable energy get to Z&E. So they called for reductions every 5 years. It drops. The tool continues to reference CBEX just for consistency in dropping to zero by 2030. So the EPA Target Finder used CBEX, but is about to change to a newer edition of CBEX. So CBEX was going to be redone, I think, in like 2010, and then there was some big problem, and the project was never finished. So there is now a more recent version of CBEX, and the Energy Star Target Finder is going to reference that. But if you're, American Institute of Architects endorsed the 2030 Challenge, so you can get the CBEX, the more recent CBEX database, but in terms of Architecture 2030's 2030 Challenge, they just said, well, it would confuse everybody if we started saying, well, if we set a different benchmark. So that's why if you go to Target Finder, they're continuing to use the 2003 CBEX database. And I don't know if they've done it yet. No, I'm sorry, if you go to Zero Tool, they're using the 2003 CBEX. At some point, I don't know if they've done it yet, but the Energy Star Target Finder is still going to tell you an EUI, but it'll be, oh, you want a reduction against the CBEX database, so they'll be using a different one. Right. So I'll get you a link so that you can actually see the CBEX data. I hope I didn't answer that in too complicated a way, but I'll find you the CBEX database.
So having done the Architecture at Zero competition for the last 2 years with students, they do give you a reference guide to EUIs for different building types. So that will be available to all of you once that's published on the website. So that might be the first place to look. And then from there, there'll be these other resources that we'll have access to.
Thanks for your attention.
Thank you. Thanks for setting up so quick.
Next week is the same rundown?
Yep.
This area?
Yep.
Okay, cool.
And I may do a